This is section 17.6, Solubility Product Constant, KSP. It is not just the solubility, it is the solubility product constant. If you take the saturated solution of ionic compounds, let's say you have a salt, and if it is a saturated solution, means you will see some solid NaCl and NaCl in the form of ions in the water. So that means the saturated solutions. So the saturated solution, in the saturated solution, these dissolved ions are in equilibrium with the undissolved ion, so forming a heterogeneous equilibrium. Why heterogeneous? Because salt is in the solid form, and for ions we write down aqueous. These equilibria have equilibrium constants, and they are known as solubility product constant. So that goes, the term goes here. So for example, a saturated solution of lead iodide. Now lead iodide is so if we are writing is equilibrium, so solid lead 2 iodide is in equilibrium with its aqueous ions. Now you have to make sure the equation is balanced. Lead can have a 2+ charge or 4+ charge. Looking at this formula, you can tell that it is lead 2+, and iodine 7th A group has 1 negative charge, so lead 2+ iodide, but since there are 2 iodine, so you put 2I negative. So if you look, this is an equilibrium reaction, and if it's an equilibrium reaction, we can always write down an equilibrium reaction constant, which will be KSP equals concentration of products divided by concentration of reactants. Now in this case, the reactant is solid, and the solid lead iodide does not appear in the expression. We do not put solids and liquids. So what will be KSP equals to concentration of lead ions times concentration of iodide ions raised to the power second. So this is the equilibrium constant expression for lead iodide. So let's take another example. For example, barium phosphate. These are ionic compounds, but their solubility in water is very low. So and they are present in the ionic as well as in the solid form. Barium phosphate now at this time I'm expecting from you that you know these formulas, how to write down these formulas. Barium has 2+ charge, phosphate has 3 negative, and you just swap the charges. And again, this is solid, so it is going to be barium ions barium 2nd A group and phosphate ions and then you balance them. There are 3 barium and 2 phosphate ions. So let's write down the KSP expression. It will be barium, concentration of barium raised to the power 3rd times phosphate raised to the power 2nd. Let's look at this question. A saturated solution of iron 2 sulfide contains 4 times 10 to the negative 10 molar ferric ions and 4 times 10 to the negative 10 sulfide ions. Now equation is already balanced, 1 Fe on both sides and 1 sulfur on both sides, 2 + 2 negative. So what will be, the question is calculate the KSP. So KSP is equal to concentration of Fe2 plus times S2 negative, multiply both of these, and it will be 1.6 times 10 to the negative 19. So this is the KSP value. So KSP is a basically measure of compound solubility. It is not a solubility, it is a measure of compound solubility. Lower KSP values, they are generally indicative of lower solubility. Why? Because that means the less the less amount of ions are formed. But when you are comparing the KSP values, you have to make sure that you are comparing the cases that produce the same number of ions in solution. So let's see what that means. For example, you can compare the KSP values of calcium sulfide and magnesium sulfide. They are comparable. Why? Because these solids, both of them, they break down to produce one cation and one anion. So yes, you can compare the KSP values of these two. Coppers, next is, but you cannot compare calcium sulfide with sodium sulfide because this is 1 plus 1 negative, this is 2 plus 1 negative, so that means we cannot compare calcium sulfide KSP value with sodium sulfide. Now use the KSP values in table 17.2 to predict the relative solubilities of CuCl, cuprous chloride, cuprous bromide, and cuprous iodide. So cuprous chloride, cuprous bromide, cuprous iodide, and their KSP values, and these values are dependent on temperature at 25 degrees Celsius. Let me see, CuCl is 1.72 times 10 to the negative 7, CuBr is 6.27 times 10 to the negative 9th, and CuI is 1.27 times 10 to the negative 12th. So if you can we compare their KSP values? Yes, because all these three compounds they break down to produce one cation and one anion. So the highest KSP value means most soluble because it is breaking down more to form the ions. Or you can say the lowest KSP value means least soluble. So here in this one, CuCl has the highest KSP value because the lower negative charge in the power. So CuCl has the highest solubility in water, then CuBr, and then CuI. Now KSP and again as solubility, they are not same. Basically you calculate KSP from the KSP expression. Solubility is simply the amount of substance that is dissolved in a saturated solution. And if we talk about molar solubility, means the number of moles of the substance that can dissolve in 1 liter of the solution. Now what you can do is you can calculate the molar solubility given the KSP value. So here, so for example, we are talking about barium fluoride here. So let's write down the barium fluoride expression first. Barium fluoride in equilibrium, let's write on solid here, 2 plus aqueous plus 2 fluoride ions. Now we can see the equilibrium here. That means what do we need to do first? We need to make the ice table. Remember, for acid dissociation or the base dissociation, you were drawing the ice table. So in the ice, this is the way I'm going to draw it here so that I can use this equation. Solid is always present in excess. Now here in the starting, initially, you do not have any ions. And let's say you have X of dissociating to form these ions. So now make sure one is the barium fluoride and barium ion ratio is 1:1. So if you have X moles are dissociating, then X moles of barium ions are forming. If X moles of barium fluoride are dissociating, then 2X moles of fluoride ions are forming. And what will be the equilibrium? X 2X. Since this will not be included in the our equilibrium constant expression, we are going to ignore it. So now write down the KSP expression first. KSP is equal to, go back to your original equation, barium ions times the concentration of fluoride ions raised to the power second. And now plug these barium ion, now plug these values. Barium ion is X times 2X raised to the power second. So this will become 4X cubed. Now this KSP value of barium fluoride in the test, it will be given to you. It is 1.84 times 10 to the negative 7th. So this, I'm making it equal to the KSP value. And from here we can calculate X. First you divide by 4 and then you take the cube root. You will get 3.58 times 10 to the negative third molar. So this is the molar solubility of barium fluoride. So what does that basically means? A saturated solution of barium chloride contains 3.58 times 10 to the negative third molar barium ions. And how many will be fluoride ions? It will be 2 times 3.58 times 10 to the negative third fluoride ions. So again, this answer, this is the molar solubility of barium fluoride. But what that means, that you need to make sure that the molar solubility of barium fluoride is 3.58 times 10 to the negative third molar, which means a saturated solution of barium fluoride contains 3.58 times 10 to the negative third molar barium ions and 2 times 3.58 times 10 to the negative third molar fluoride ions, and this will be 7.16 times 10 to the negative third molar. Now in the last problem, the KSP was given and the question was to find out the molar solubility. In this question, the solubility is given and it is given in grams per liter, and you have to find the KSP, the opposite. When we are talking about KSP, we are talking about molar concentrations. So the first step is convert this barium nitrate solubility, which is given in grams per liter to moles per liter. And for that, first thing you need is the molar mass of barium nitrate. And molar mass of barium nitrate is 261.338 grams. You can just add the atomic masses. So that means if you have 27.50 grams per liter solubility, so 261.338 grams equals 1 mole. So that will be 0.1052 moles per liter. So first step is to convert. If the solubility is given in grams per liter, you have to convert it to the moles per liter. If it is given in moles per liter, then you don't have to do this step. The next step is that you write down the equilibrium expression. Barium 2 plus charge, nitrate 1 negative charge, and 2. This is solid, aqueous. And then you construct the ice table. Excess 0 0, negative x, and since there is 2 here, we're going to put 2x. Then we have x concentration of barium ions and 2x of the nitrate ions. Next step, write down the KSP expression, which is equal to concentration of barium ions times concentration of nitrate ions raised to the power second, and then plug these values. Barium ions is x, nitrate is 2x raised to the power second, which is equal to 4x cubed. Now so basically what this x is, it is the molar solubility. How many moles of barium ions are dissolved. That's the molar solubility, and which we have it here. So 4 times x is 0.1052 raised to the power third equals 4.66 times 10 to the negative third. So the two things, given the KSP value, you should be able to find the solubility in grams per liter or in moles per liter, or given the solubility, you should be able to find KSP.